Gets it all. All right. So let's remind ourselves of the last thing we talked about. The last thing we talked about were variants of Turing machines, and we pretty much proved that no matter how you tried to fidget a Turing machine, it's still a Turing machine. We couldn't come up with some way to somehow make a Turing machine suddenly able to solve more problems than it already could. So the stupidest computer on Earth and the smartest computer on Earth still can only solve the exact same problems. One solves them much more faster, much more efficiently, and practically speaking, it can solve problems that the other one can't. But theoretically speaking, it can't. The other one, if you gave it enough time, enough memory, it can solve all the same problems. Quantum computing doesn't change that, non-determinism didn't change that, nothing changes that. So we can't figure out a way to make a Turing machine more powerful than it already was. So that's one thing to remind ourselves of before we jump into this. The last thing to remind ourselves of is to talk about the difference between a Turing recognizable language and a Turing decidable language. So for a Turing recognizable language, that was a language that a Turing machine could accept the strings. It could say, yes, accept that string. If I could build a Turing machine that could say, yes, accept that string, then we could recognize the language. A decidable language could recognize the strings in the set, when they're in the set, but also reject the strings that aren't in the set. So we look at our bullseye. Here's all the recognizable languages. Then the decidable languages are a subset of that. If it's decidable, it's definitely recognizable, but if it's recognizable, it's not necessarily decidable. So a language is recognizable if a Turing machine can accept every string in that language. It's decidable if it can accept every string in that language and reject every string not in that language. So now we're going to kind of jump gears and come at this from a more historical approach. How did all these Turing machines even come into existence? What was going on? Why do we even use these mathematical constructs? What's the point of them? So to understand the point of it, we need to know what Alan Turing and Alonzo Church and these guys were trying to do. Ultimately, what they were after was a definition of algorithm. What is an algorithm? Now, prior to Turing and Church, we had good intuition for what an algorithm was and what people meant by an algorithm. If you saw it, you knew it was one. It was pretty easy to detect. We had the notion of, for those of you who did discrete math, Euclid's algorithm for finding the greatest common divisor of two numbers. It was an algorithm. We knew it was an algorithm. It was some finite set of procedure that you could follow through, and it gave you some solution. But with Hilbert's problems, just having an intuition for what an algorithm broke down. Because yes, we knew what an algorithm was when we saw it, but could we prove that no algorithm exists for a specific problem? No. We needed an exact definition of an algorithm so that we could prove no algorithm exists. So if an algorithm did exist to solve a problem, you would know it if you came up with the algorithm. But how would you go about proving no algorithm existed to solve a problem? That's where we really needed a definition of algorithm. And so, introduce you to the problems that kind of set off the thinking. So in the year 1900, Hilbert, famous German mathematician, for those of you who have done geometry with Brother Colley, and he uses Hilbert's axioms, same Hilbert. So he was at this conference, famous conference, and he presented 23 problems to the world that he said, this century, let's make these the 23 problems to solve. So from the year 1900 to the year 2000, let's focus on these 23 problems and get these 23 problems solved. And what were these 23 problems? Well, I'll give you a sense of some of them. Problem number one was to show that there is no set A such that the size of A is between the size of the integers and the size of the reals. Conclusion, you can't prove this. It's been proven that you have to accept as an axiom one way or the other. Problem number two, prove that the axioms of arithmetic are consistent. Those who know Gödel's theorem know that he proved that they can't be, you know what consistent means? The axioms of arithmetic are consistent. It means that you can't prove some contradiction from the axioms of arithmetic. I can't prove 5 plus 5 is equal to 10 and 5 plus 5 is equal to 11. That would be an inconsistent system.
Can you remind me what, in this context, axiom means in arithmetic?
The axioms of arithmetic, that's just the associative property, the distributive property. If you don't understand exactly what these are, we just care about the 10th.
Okay.
I'm just plugging some of these in for you to help you see what some of the problems were. And once again, this was a problem that it turns out you can't prove. And Good will prove that you can't prove it. Kind of. And so he gave all these problems that he wanted solutions to. And a lot of the problems we proved that actually there's no solution. He wanted us to be able to say yes or no to this question. And the answer was you can't say yes or no to a lot of the questions. And so here's another one where we have the same problem. He said, he didn't use this exact phrasing. Plus he was German, so obviously he didn't use this exact phrasing. But roughly what he asked was, find an algorithm to determine whether a given Diophantine equation has a solution. What's a Diophantine equation? It's just some polynomial in terms of however many variables you want, like this, where all your coefficients are integers, and the only solutions we care about are integer solutions. So write some polynomial, doesn't matter what the polynomial is, over here, in terms of however many variables you want, x, y, z, w, doesn't matter. With only integer coefficients, the coefficient of that's -1, -10. A Diophantine equation is, take some polynomial like that, set it equal to 0, find integer solutions. That's a Diophantine equation. So the question would be, in this context, given this problem, are there some integers I can plug in for x, y, and z that make this equation true, yes or no? And with this specific example, it just so happens that there's a solution x equal to 5, y equal to 3, z equal to 0. Now, how could we have come up with those numbers from that equation? Is there some systematic way to do it? Is there some algorithm such that no matter what Diophantine equation I gave you, you could write some algorithm that ultimately would be able to say yes or no, there is some solution. It doesn't necessarily have to find the solution, it just needs to be able to say yes or no, is there a solution? That was the problem. That's Hilbert's 10th. Pretty famous one, and it's referred to that way a lot, Hilbert's 10th. And the answer to the question is, bad question. There is no algorithm. And provably, there's no algorithm. And so to prove that there was no algorithm for this, required us to have a concrete definition of what exactly we meant by algorithm. Intuition no longer worked. So I give you some of the backstory to why they were thinking about these types of things. So it was proven that the 10th, Hilbert's 10th, has no solution, but it required a precise definition of algorithm to prove that it doesn't have a solution. And unfortunately, we will not be able to prove that it doesn't have a solution because that's a semester course in and of itself. But it is a course that you can take, which is just understanding that proof, and it would be a ton of number theory. Okay, so some of the historical background. So now we fast forward 36 years. So now we're in the year 1936. And a guy by the name of Alonzo Church wrote a paper where he proposed a definition for this word algorithm. Everyone has great intuition for what they mean by algorithm. So now what people are trying to figure out is, can we come up with a precise definition that encapsulates all these meanings that everyone has had? Everyone from Euclid all the way down to Hilbert. What everyone has meant through all time by this word algorithm, can we come up with something that encodes that word algorithm? So Alonzo Church came up with a proposal using what we call lambda calculus, and basically right after him, his pupil, Alan Turing, did the same thing. And he proposed a definition of algorithm using Turing machines. Turing machines are more intuitive than lambda calculus. They're easier to think about, easier to reason about. And so that's why when we went through this course, we used Turing machines. We could have done it all with lambda calculus, and it would have been logically equivalent. It's just Turing machines are easier for us to use. So we use Turing machines. And it's part of the reason that Turing became a lot more famous than Church. It's because it was just easier to reason about his way of talking about computation. But it turns out what Church proposed with his lambda calculus and what Turing proposed with his Turing machines were logically equivalent. So Church says it should be this definition. Turing says it should be this definition. And it turns out their definitions are logically equivalent. anything that one definition calls an algorithm, the other definition does, and anything that one doesn't call an algorithm, the other one doesn't. They're logically equivalent definitions.
And Turing didn't purposely do that after reading Churches?
They were working together, so they were teacher-student type relationship in their research. Church is the older of the two. So Church published it since they were working together. I mean, they weren't like trying to get to the punch first, right? So there wasn't any hard feelings between the two of them that Turing's is the method that took off. I'm sure there was a lot of back and forth collaboration. So they were both working on the exact same problem. There's a second reason that Turing's version took off, which we'll talk about at the very end of this section. But there's nothing special about his, it's just easier for us to think about. And so, that's what the Church-Turing Thesis is. So in 1936, Alonzo Church and Alex Turing proposed a definition of what we mean by the word algorithm. Church using Lambda calculus, and Turing using Turing machines. He didn't call them that, but that's what we call them now. This thesis is not a proof that this is what an algorithm is, but a claim that what history has meant by the word algorithm is captured by their definitions. And some other people have come up with other proposed definitions for algorithm, turns out logically equivalent. So these aren't the only two that have done this, a few people have done it. Every time someone comes up with some new clever way that gets at what we mean by algorithm, it turns out to be logically equivalent. This seems to be a very robust definition. So it seems to work. So that is currently our definition of algorithm. Essentially, what's an algorithm? It's what a Turing machine can do. Now, his famous paper is called On Computable Numbers, if you care. It's on computable numbers with special application to some big German name problem, which is basically on computable numbers with a focus on the halting problem, for those of you who have already seen the halting problem. But there's the actual paper if you're interested and want to go look at it. Somewhat readable. He uses language different than we do, so somewhat not readable as well. And he uses a lot of tables rather than nice diagrams because he's typing it up on a typewriter.
Oh, wow.
Tables are a lot easier than diagrams. So, hard to read, but still somewhat readable. Anyways, so now let's do a little bit of a deep dive into Hilbert's 10th, this problem right here. Now I told you that we can't solve this problem. We're not going to prove that it's undecidable, not a chance. But we're going to prove that it's at least recognizable. We could come up with an algorithm such that if you gave me an equation that did have a solution, then I could find the solution. That's what we're going to do. So we're just going to prove that it's recognizable. So this language, the set of all Diophantine equations is not decidable, but it is recognizable. You could build a Turing machine to recognize solutions, to come up with solutions to the problem, but you cannot build a Turing machine to say, no, that problem has no solutions. You might be able to do it in specific cases, but there's no general formula, there's no general algorithm that will work no matter what Diophantine problem I give you. Make sense? Unfortunately, we're not going to prove that latter part. But we'll prove it's at least recognizable. Well, we'll prove it. We'll give you two special cases and then say, and you get the point. All right, so let's dive into it. So, focusing on Hilbert's 10th. Let D be the set of all polynomials P, where P is a polynomial with integer roots. Or in other words, P is one of these things. It's the left-hand side of the Diophantine equation. The Diophantine equation is a whole equation. We're talking about this left-hand thing. And when we say integral roots, the roots of a polynomial are the numbers that make it 0. So this is the set of all these types of polynomials with an integer root. Or in other words, it's a set of all these polynomials such that there are some numbers you can plug in that make the whole thing equal to 0. Make sense? So being able to recognize this set, being able to recognize this language, is logically equivalent to being able to determine if all these problems have a solution, yes or no. Right? That's why I tell you that there's no difference in math when we talk about finding solutions to a problem. In computer science, we just call it, or in computation theory, we just call it recognizing the language, solving a problem, logically equivalent. Recognizing if this thing has solutions is identical to recognizing this language. So let D be the set of all these types of polynomials that do have integer solutions, or in other words, that have integer roots. Roots are the numbers that you can plug in that make the polynomial go to 0. Then the question becomes, is D decidable? That's another way that we can phrase Hilbert's tenet. If it's decidable, then we could design an algorithm that says yes, every time one of those polynomials does have integer roots, and no, every time one of those polynomials does not have integer roots. Make sense? Okay, so that's our rephrasing of Hilbert's problem in more computation-friendly terminology. And the answer is no, it's not decidable, but yes, it is recognizable. We'll do the recognizable. First, we're going to do a special case. We're going to start with D1, D sub 1. What's D sub 1 going to be? It's going to be all the Diophantine equations where we only use one variable, called x. So you're not allowed to use y's and z's, just x's. So let D1 be the set of all polynomials p, where p is a polynomial, over x. A polynomial over x just means it's a polynomial where x is the only variable that shows up, with integer roots. So this would be something like 3x squared minus 27, there's 1. And does that have an integer root? Yes. If I plug in 3 for x, it gives 0.
When you say for integer root, if you had something like root 2, then it would not be a Diophantine equation.
X squared minus 2 is not a polynomial with an integer root, because its roots are plus or minus the square root of 2, which is not an integer. This is a polynomial with an integer root, namely 3. This is a Diophantine equation.
Because you can divide
The Diophantine equation has a solution when you plug in 3, or in other words, this polynomial has a root at 3. Those are logically equivalent statements.
Okay.
Make sense? So we're talking about things like this are what are in D1. Only one variable.
But I could have any power that I want, right? Like I could have
Yes.
x squared plus x cubed
Yep.
plus x to the 4th.
So in general, well, not in general, but write some other one here. X cubed plus 27x squared minus 54x. P of x could be something like that. Does that have integer roots? I have no clue. Maybe.
What's the integer root of the example in number 10? Like,
Right here,
yeah.
the integer root is x equal to 5, y equal to 3, z equal to 0. If you plug in these 3 values for your variables, then this thing right here will evaluate to 0.
So integer root simply means all the variables are integers.
No. An integer root means all the variables are integers, and when you plug it in, it evaluates to 0. That's what the root of a polynomial is.
So if it doesn't have a solution, then it's not a Diophantine equation.
Correct.
Oh.
Okay.
Or
Or
if
we'd
the
say
root
the
is not-
Diophantine equation has no solutions.
Or if the root is not an integer,
Or if the root's not an integer.
like 1/2,
Right.
then it's not.
Right. We pretend that our domain for the function is just integers.
Because if you didn't bound it to integers, if you said it could be anything, then like
Then there's always,
then you'll always be able to find something even if it's imaginary.
right.
So why are we focusing on integers? Could you prove that if you took all the real numbers, could you find an algorithm for that?
Yes. Kind of. We've already talked about that one a little bit. The counterpart to this is give you one with the real numbers. So with the real numbers, you know that if I have ax squared plus bx plus c equals 0, I can always solve that. And I can solve that with the equation x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Coming up with a formula and coming up with an algorithm identical. So, yes, we can always solve ones like that, no matter what a, b, and c are. If you allow imaginary numbers. If you haven't seen imaginary numbers, just take my word for it. Now, what about if we have a cubic? What about if we have something like this? If I would have had ax cubed plus bx squared plus cx plus d is equal to 0. Can we do it with that? Yes, there's a similar type of formula. It's a big monstrosity, and it'd take me this much space to write it out, but yes, there is one. Okay, what about if we got this? Ax to the 4 plus bx cubed plus cx squared plus dx plus e equal to 0. Does that have solutions? Yes! And the formula is ginormous, and it'd take me this whole whiteboard to write it out. But it's there, and we have it, and we can do it. What if I go to a 5th powered polynomial?
Still there.
No. No more. 5th, 6th, 7th, 5 and up, no more solution. And it's provable, no more solution. Similar to how this is provable.
Okay.
So, different problem, but yeah. Still gets to a point where it's undecidable. Alright, so why are we focusing on this? It's a special type of Diophantine equations. You haven't seen them yet, but they're of very special interest in number theory. You know them a lot.
So I assume like the reason why we went down this path was we just proved Hilbert's 10th is wrong because we took a subset of Hilbert's 10th and proved that we can find some cases where we cannot deterministically say whether or not it has whole number roots.
No. So this is undecidable,
Right?
and we're just keep saying it's undecidable. No proof, no justification.
But didn't we just prove that the special case is also undecidable?
I'm going to prove that this is recognizable. I'm telling you that you cannot come up with an algorithm, no matter how hard you tried, that if I gave you a Diophantine equation, your algorithm determines, does it have solutions, yes or no? That algorithm, impossible, doesn't exist. However, if I promise I'm only going to give you Diophantine equations that do have solutions, you just have to write an algorithm that finds those solutions, then yes, you could create that algorithm. That one we call recognizable. So proving that the first algorithm can't be written, we're not going to do that. You just have to take my word for it, or the word of the author, or whoever. The second one, proving that's recognizable, that you could come up with an algorithm for finding solutions if solutions exist, that I'll prove to you. And so we're starting out with a special case where we don't want x's and y's and z's. We're going to limit ourselves to just x's, to just things like this. Make sense? All right. So D1 is a set of all polynomials P, where P is a polynomial over X with integer roots. We're going to prove D1 is not decidable, recognizable.
Okay, that's what was really confusing me.
Yeah. Okay. Yeah, I make a lot of errors like that. All right. And how can we test this? What would our algorithm do? What would our machine do? So our machine we'll call M1. And now, I told you that we're done writing nitty-gritty what a Turing machine is. We're not going to write the state machine anymore with all the diagram arrows. You remember doing just 0 to the n, recognize 0 to the n, 1 to the n, and how ugly that thing was. So trying to do Turing machines for something like this, it would just be atrocious, not a chance. So we're just giving high-level descriptions of how these machines would work. So how would M1 work? Here's what it would do. And we put quotes there to remind us, hey, we're just giving a word description of how this would work. This is not a precise definition. Okay, so how would our machine M1 work? So it would take as an input the polynomial. Now you'll notice I put brackets around that polynomial. What do those brackets mean? That means we treat the polynomial as a string. Remember that a Turing machine can only take strings as inputs. It can't take a polynomial as an input. But for those of you who are programmers, it's really easy to convert a polynomial to a string, right? There we go. That's all we're doing. So some string encoding of the polynomial. There's a trillion ways you could do it. There's not one right way to do it. Just somehow representing the polynomial as a string that the Turing machine knows how to understand. Okay, so on input, the polynomial encoded as a string, where p is a polynomial over x. Here's what we do. We simply evaluate p with x taking on the values 0, negative 1, 1, negative 2, 2, negative 3, 3, negative 3, 3, negative 4, 4. Dot, 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 going on forever, and except if p of x is ever evaluated to 0. So I have my polynomial. I can plug 0 into the polynomial and see what I get out. If it spits out 0, I'm done. If it doesn't spell 0, what do I do next? I plug in -1. Then I plug in 1. Then I plug in -2. Then I plug in 2. And if it turns out that the secret root that we're looking for was the number 157802164 and maybe that was the thing that made this thing 0, my little algorithm, churning away with enough time, will eventually test that number. And it will find that solution. Now, if there was no solution, my algorithm's going to run forever. Right? So if you give me one that has a solution, I'll find it. So I'll just recognize the language. I won't decide it. That make sense?
I do have a question on term. When you say polynomial over x, do you mean it just has the
Like this.
variable x? Okay, yeah.
And not like that. I was going to say single variable polynomial. I didn't know if that was harder language. I don't know. Anyways, notice that the only trick to this problem was trying the integers in a very specific order. If I would have said, first try all the positive integers, then try all the negative integers, that wouldn't work. Because I can't ever finish trying all the positive integers. So if the answer was -1, we would have never gotten around to -1. So we have to come up with some clever way of listing out the integers to make sure that we will eventually get to any integer you state. That was the trick to the problem. Might seem kind of stupid obvious, but that's the part that you would have had to think about a little bit if I made you do this yourself. Once you got that, you would have been fine. So then, M1 recognizes D. It recognizes D1, and we're done. And so this is how we'll be doing our proofs that languages are recognizable or decidable until we get to reducers. And it will be very high level like that. We won't be drawing any diagrams. Which is why I'm saying it's a good time to jump in.
So if you were to just put like one constraint on the 10th, like the roots are less than some number or greater than some number, then instantly it's decidable as well.
Yes, and actually that is how this problem is proven to be undecidable. It's proven that there are no bounds. So special cases of this are proven to be decidable because there's ways that you can calculate the bounds. But once you get to, I don't remember the complexity, I don't know if it's 2 variables or 3 variables, then it's proven that you can no longer calculate upper and lower bounds. So, yeah. Okay, good with this. Ready to move on to a slightly more complicated example?
Yeah.
Alright, so now let's move on to 2 variables. We did it with 1 variable, let's prove with 2 variables it's still decidable. So if D2 is a set of all polynomials P, where P is a polynomial over X and Y now, with integer roots, then D2 is still recognizable. That's what we're going to prove. With me? Okay, what are we going to do? We're going to, on input, some string encoding of a polynomial, where P is a polynomial over X and Y. We're going to evaluate P with X and Y, where the XY values come from, dovetailing the given table. I'll explain that here in a second. If P of XY is ever equal to 0, then we accept. So we've got to come up with a way of plugging in combinations of X's and Y's that make sure we try every combination of integers. Right? Let me give you a bad way of doing this. Let's try 0 for X, 1 for Y. Then 0 for X, or let's try 0 for X, 0 for Y. Then 0 for X, 1 for Y. Then 0 for X, negative 1 for Y. Then 0 for X, 2 for Y. Then 0 for X, negative 2 for Y. ... to infinity. We only are ever trying 0 for X. That's a bad way to do it. So we need some way of plugging in, some systematic way like we had here, of plugging into our equation so that we're guaranteed to try every combination of integer. So if you come over here, write some random combination of integer, say the solution was X equal 2587 and Y negative 649, whatever our method is for trying all possible integers, we need to eventually try this one. You with me? Okay, and the way we do that is called the dovetailing method. So, I don't know which one you want to think about, X's and Y's. We'll think about these up here as our input for our X's, and these down here as our input for our Y's. So this square symbolizes plugging in 0 for our X, 0 for Y. This square symbolizes plugging in negative 1 for X, 0 for Y. This square symbolizes plugging in negative 2 for X, 2 for Y. With me on the interpretation? Okay, what order do we try these in? we do a dovetailing. We start with 0, 0, then we try these 2 squares, then we come down and we do these 3 squares, then we come down and do these 4 squares, then we come down and do these 5 squares, and that's the order that we try it in. And that's a way of coloring the grid that if we follow that pattern coloring the grid, we'll eventually get to any square on the grid. And so that's the trick, that's the method. Now that was a 2-dimensional dovetailing. You can imagine a 3-dimensional dovetailing now, where we spiral out covering all 3 dimensions. And a 4-dimensional dovetailing and a 5-dimensional dovetailing. And so with that, it doesn't matter how many integers we're over with this or how many variables we're over with this dovetailing method. You just increase the dimensions and dovetail over it. And you'll eventually get any combination. Does that make sense? So that's our proof that it's recognizable. Any questions on the recognizability of that before we move on to the next topic? And this dovetailing method, it's important you become comfortable with it because it comes up a bit in computation theory.
Is it like
Very
the
useful.
only solution, or is there lots of different ways you could go about it?
There's lots of different ways you could go about it, but what you're going to have to do is come up with some method for coloring in the grid that's guaranteed to get to every square. If I tried to color in the grid by going along the top all the way before I go to the next line, I'll never finish going across the top. And so I can't do that. And so there's some ways of coloring in the grid that are guaranteed to get all the squares, and other ways of coloring in the grid that aren't. Kind of weird.
This is just the most simple pattern to accomplish that task.
Right, this is just some simple pattern you can easily get. You can come up with some complicated thing that says do this one, then this one, then this one, then this one, whatever. That happens to get them all. I don't know.
Technically, you could just randomly pick points.
I was just thinking about that. I'm not sure because you have infinite options.
I guess so. So I guess the chances of you picking any point
Is 0.
is 0.
Right? So I was thinking about that. Because I thought, is that true? I'm not sure. So I'm not comfortable saying that's true.
I want it to be true.
But yeah, there's a stupid fly. All right. So that covers that.
So are you going to explain why you couldn't do 3 polynomial? You couldn't recognize 3 polynomial things?
You could. That's what I'm saying. You could. Now imagine we made like a 3-dimensional cube, and we could go through all the squares on the cube with this dovetailing method.
Okay, yeah.
And you can't imagine a 4-dimensional cube, but if you pretend you can imagine a 4-dimensional cube,
You could?
yes, you can do it with 4 dimensions, 5 dimensions, 6 dimensions. So it doesn't matter. This is always recognizable. It's not decidable, and we won't prove that, but it is recognizable, and that is our half proof of that.
Okay, yeah.
Make sense? Okay. Alright. So a note, I already made this note, but make it again. From here on out, we're interested in algorithms, not necessarily Turing machines. The Turing machine only serves as a precise model of computation. So when we need stuff to be exactly precise to set up our higher level notions, we use the Turing machine, but once we get those higher level notions, we're kind of done with the Turing machine. Because we could just as easily use lambda calculus or something else. And what we really care about is just the algorithms. So the Turing machine was just a means to get into the algorithm. Okay. Now, some of the historical consequence of Alan Turing's paper and some notes. So historical note, Enigma. How many of you are familiar with Enigma? Imitation Game, have you seen Imitation Game? You haven't seen Imitation Game?
I want to, but I have not yet.
I don't know how much we care about Enigma. Try and give you...
Talking about the machine, or are you talking about the word Enigma?
No, oh, sorry, the machine. The machine. The encoding machine that the Germans used during World War II, Enigma.
I've
That machine.
watched a lot of videos on it.
You watched a lot of videos on it. Okay, so you're very comfortable with Enigma.
Yes.
And him, not so much. Alright. Back when you were a 3rd grader, and you made some little secret language with your buddy, did you do? You built some dumb table where you had A, B, C, D, ... Z. And then underneath that you had C, A, D, F, ... Y. And you're saying, this letter goes to this letter. So you wrote using these letters, and then your pal could decode it using your key.
Yeah.
Alright, so an Enigma machine had a bunch of rotors in the machine. Had 3 of them. That did this very thing. So you plug in over here, one wire to your A plugs in right there, and this wire inside the machine comes out like right there, which if it comes out on your 17th hole, then it came out at Q. Right?
Yeah.
So you had a rotor, and it had 26 of these rewiring, so it's rewiring all these letters. Let's just focus on one rotor for a second, and then we'll introduce those other ones in a second. So this does exactly what you did over here with your pal. It rewires them all. Now, this is a rotor inside a big typewriter. And what happened was, every time you pushed a key on the typewriter, the rotor rotated one. This is a wheel that rotates. And so it changes the wiring. So every time you press a key, it's like every time you press something on your keyboard, the rotor turns, and it's a different wiring up of how letters match to letters.
Okay.
And since there's 26 matches, you'd have to push a key 26 times to get back where you started. The second thing that was nice about this rotor is if it matched A to Q, it also mapped Q to A. So the way that it would work is you would take a message, you would type it out. When you pushed A, it would go to Q, and the Q would light up on the screen, and you write Q on a piece of paper. And then the wheel would turn. And then you press B, and maybe now B also went to Q, and so then you write Q again on a piece of paper, and the wheel would turn. And you keep writing out your message. Your bud, when he got the message, you and him prearranged how you hook up your rotor. You agreed to start the rotor in position 17. So then he would type in your weird message, and then write down the letters that light up as he types out your message, and it would be back to the initial message. Does that make sense? Kind of, yeah. So that's one rotor. Now, that's not really how it worked. They had 3 rotors in here. So this wired into this would rewire out to right there, this would rewire out to right there, and every time you push a key, this one spins. This one has 26 positions it can be in before it's back to where it started. So once it spins 26 times, it makes this one spin once. And then once this spins 26 times, it makes this one spin once. And so there are 26 cubed possible arrangements of those 3 rotors.
And it would never reset a day because they would do it all over.
Right, and every day you tell your pal, put your first wheel in position 17, your second wheel in position 5, and your third wheel in position 6. You come up with some big table of just 3 numbers on how to organize your rotors, and then do that each day. Encoding your secret messages to each other, right? Even better than that, this rotor's not the same as this rotor's not the same as this rotor. And so you can actually change the position of the rotors as well. So you can name this rotor A, you can name this rotor B, and you can name this rotor C, and you can tell them, make sure you have A, B, C, or maybe another day you want it to be C, A, B, or another day you want it to be B, C, A, whatever. So you also had times 6 ways that you could arrange those 3 things. Right?
So, if 2 people have these, they both have to have them in the exact same setting.
Right. So you and I, first we get together. We say, here's our settings. We write them down on a piece of paper based on each day. We're going to change it each day. And then you have your paper, I have my paper. Now we separate. Now, I can type out my message and send it to you. Doesn't matter who sees it while I'm sending it to you. It's just a bunch of gibberish. Once you get it, you can decode it.
And you have to type all the letters on yours.
You have to type all the letters on yours and the message comes out.
So is there like 2 sides for keys to be on?
Yes, you have to have a key and I have to have a key for how we arrange these rotors. But if you have a key and I have a key, then as I type messages to you and the mailman goes and delivers a message to you, it doesn't matter if he looks at it. He's not going to get any information from there.
So if you write like cat and has 3 Qs, you would go to yours and type in 3 Qs. How would you know that that says cat?
Because of configuration.
So I go to mine and I type C. So over here, I type in a C. That goes through the first wheel, goes through the second wheel, goes up through the third wheel, and I say, well, all said and done, it came out Z. So I write Z on the piece of paper.
Okay.
That piece of paper goes to you.
Oh.
If you put this in the exact same configuration that I did, and you push Z now, then C is going to light up.
Going on.
And you're going to write C now.
The letters always correspond to each
The
other.
letters, yes, that's how it was designed. So the letters always
Okay.
correspond to each other.
I missed that part.
Right. So if C is ultimately mapped to Z here, then that means Z here is ultimately mapped to, oops, got to go up for C. C.
Well, hold on. So it is possible, I believe, that the configuration come back with the same letter multiple times, but actually mean something different.
Right. But now, once I push my C key, what happens? This wheel turns. And now that completely changes the wiring.
Yes.
And now C is now mapped to a completely different letter.
And that means
But when you were decoding, when you pushed Z, that also turned the router and kept it in sync with mine.
So what tells you C? What tells you, after you click Z, what tells you that there's a C?
It has a light that lights up certain letters at the top.
Okay.
So you push C on the keyboard and it lights up a letter on the top. That's how I knew to write Z. I pushed C and it lit up Z on the top. And if I would have pushed Z, it would have lit up C on the top in that same exact position.
So because configuration changes every letter, you could technically, it could say Z, 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 Z. And
Yes, it
actually-
could technically say that.
Also, theoretically, would there be a combination in a message where the encoded value would be the original message?
Yes.
Yeah.
Oh, wait, no.
No, not possible.
Not possible, which was actually one of the reasons that Enigma was able to be broken, is a key never mapped to itself. And so that was one of the insights Alan Turing got to help him decode these machines.
Did he end up decoding it?
You did.
Yeah, but we haven't even got to the hard stuff yet. This isn't what the Germans were using. This is what bankers were using. This is what your regular Joe was using for his regular encoding
It wasn't your
to keep the mailman from snooping in his mail. This isn't going to stop the US military or the English military. No, that will stop the mailman.
Okay.
So, this is a regular one. That just had 26 cubed times, there's 6 different ways that we could arrange those, 3 factorial ways that we could arrange the 3 routers. So times 6 ways that we could arrange that. Now, what the German military did is they used the same machine. So they had 26 cubed, possible different ways that they could arrange their 3 rotors. But they had 5 rotors to choose from instead of just 3. So they had 5, and then they just choose 3 of them to put in there. So you had 5 options for your first rotor, 4 for your second, 3 for your third. So 5 times 4 times 3 is 120. Did I get that right? No, 60.
So you said they had 5 rotors.
5 options for your first rotor, times 4 options for your second, times 3 for your third.
What do you mean by options?
If I have 5 objects, and I'm going to take 3 of them and put them in some order, I have 5 options for which marker goes first. Now I only have 4 options for which marker goes second. Now I only have 3 options for which marker goes third. Those are my 3 markers.
Yeah.
That would be my 3 rotors.
Okay.
5 times 4 times 3.
I see that. Okay.
So that's one thing that they did, which makes that there's 10 times more configurations, which is cute. The other thing they did, which is just a beast of a problem, is once it was all said and done going through this sync, they had a bunch of cables that randomly swapped 2 letters. They had 10 cables that randomly swapped 2 letters. And that just made the solutions here absolutely blow up. Maybe we'll calculate it in discrete math. We can do that. I just don't want to take the time to do it here because we'd have to use choose notation.
Just curious, do you know the number off the top of your head? Like, roughly
No.
what the order of magnitude is?
It's several orders of magnitude larger than this. We're talking about millions of times more complicated. So, completely blew up how complex the machine was. What was Alan Turing's job? Alan Turing's job was to come up with a machine which would basically systematically try all the possible combinations, figuring out if one possible configuration wouldn't work. And it had to just turn away, trying them all. That's essentially what it did. They had some tricks to make sure that they weren't doing any sort of repeats. It turns out testing if A maps to D is the same thing as testing if D maps to A, so there are some things that you can stop yourself from testing. But ultimately, that's what his machine was doing. Trying all these different configurations with a message to see if any of them made sense, decoding that message. So that's the bombe machine that he was building. Now, why are we interested in this bombe machine? If you've seen the movies or you've seen pictures of the machine, it's this big, massive monstrosity of a machine. Massive computer. And what is it good for? Just breaking Enigma. At this time, there is no difference between hardware and software. You coded the computer through its actual wiring. That's how you told the computer what to do. So you had this big, massive machine that they built, this big bombe machine, millions of dollars, and the second the Germans decide we're done with Enigma, we're using something else, that whole machine becomes worthless. You can scrap it for parts, there are probably some reusable configurations in there, but for the most part, the whole machine is now worthless. It's crazy. And that's how machines were designed back in 1940. Now, with Alan Turing's paper that we talked about, wherever it is, somewhere around here, in 1936, he laid out the theoretical framework for building a universal Turing machine, is what he called it, which is the same thing as a reprogrammable computer. He set down the theoretical framework for, actually, if you just have enough hardware, you can build something that can run any software. And then you don't have to engineer by running wires in something. You can engineer with code. And you can just use the code to tell the machine what to do. It's a huge breakthrough in thinking. Huge breakthrough in thinking. This notion of a universal Turing machine. And it honestly didn't take that much longer for them to start building these things. So the bombe machine that was built in 1940, ENIAC, some acronym, can't remember what all the letters are, is one of the first universal reprogrammable Turing machines. An actual physical thing. And that was done in 1945, the year World War II ended. Too bad they didn't have it 5 years earlier. And so, I don't know if this is actually the first one. There's some debate about which one's the first one, but close enough to one of them. They're all arguing for that year. It's just a matter of which one came first. So in 1945, we now officially have a physical application of what Alan Turing proved was possible in his 1936 paper. This is another reason that Turing gets so much more credit than Church does. Because Turing lays out in explicit detail the actual diagrams in all the states for how to build one of these Turing machines. And he tells you, here's exactly how to build a Turing machine, that you can give it some other Turing machine and some string, and it can run that string on that other Turing machine. And you can give it an encoded Turing machine, or a program to run. That's what a program is. It's an encoding of a Turing machine. And so, he proved that was possible, and it wasn't even 9 years until you had, well, 9 years. It wasn't even 10 years until you had an actual physical machine doing that thing. And this drastically changed the name of the game. It's huge. And to give you a sense of how computers suddenly changed the world, this machine, one of the earliest machines, so this thing is super, super stupid compared to what our computers can do today. To compare the two, it's laughable. And even this earliest version of the machine, it could solve a 20-hour problem, a problem that took a computer. We need to talk about what a computer meant in 1945. If you were in 1940, and I came up and I asked you, do you have a computer? That's like me asking, do you have an accountant? Do you have a person dedicated to the task of computation? That's what a computer was. Roughly speaking, while the men were off fighting war, the women were put in rooms doing mass calculations. During these world wars, you had rooms full of women just doing mass calculations, and it took them roughly 20 hours per problem to solve. And this would have been like calculating, doing the calculations you need for like an artillery shell to get to the right place. And I don't know, do we need to give a little bit of explanation why that's super complicated?
Artillery shell mathematics?
Yeah. I don't know. I'm just worried that someone might think, isn't that really simple?
Like why objects going faster than the speed of sound are really hard to figure out where they're going to land.
Yeah.
Or the fact that wind resistance is the
Yeah, the wind resistance, the air resistance. So these computations get absurdly complicated. And so, yeah, to figure out one of these problems took a computer, a human person, roughly 20 hours of work. That's half your work week for one problem. A work week, you get 2 problems done. This first machine, this first machine which comes up was able to solve these problems now in 30 seconds. So the first machine's able to solve what used to be a 20-hour problem in 30 seconds. Or in other words, it's 2,400 times faster. So this one machine could do the job of 2,400 people. Knock off the 400 for downtime or putting input in, it can do the job of 2,000 people. 2,000 computers can now be done by this machine.
Wow.
The ENIAC machine at the time it was built, I think cost roughly $1 million. And I think the median salary for a computer at the time was roughly $10,000. And so this machine would pay for itself in half a year. So even back when computers were stupid and computers were absurdly expensive, they were still a great investment, which is why computers just blew up from the time they were introduced. So that's the end of our historical note. We'll get back to talking about Turing machines here, unless you have any questions about this. I don't know. Maybe we could do it as class. I don't want to try and do it on the fly. I think I'd make a mistake. But do you guys want to do the calculation for how many configurations there were for Enigma? I don't think it'd be that complex. I just don't want to try and do it on the fly.
Didn't we do it?
All right. Huh?
Did we do it? 26 cubed?
No, that was just for the basic machine. We didn't do the German version of it,
Oh, with
which got way bigger
a million more, yeah.
with the plug port.
You could look it up.
Yeah, you can just look up the number.
We were on our side conversation. We were joking about multi-threading the fleshy computers, like the actual people, like splitting those problems up and along multiple threads, and wondering if they actually took advantage of some of those kinds of things.
I don't know. I would guess that they would have to.
Because like if you're in the military, you don't want to take 20
Right.
20 hours to then decide that you can finally shoot.
We need some artillery at this spot, okay? Give me a minute.
Give me 20 hours, I'll have your answer.
Or just if they could split it up, that makes more sense.
Yeah. I'm not sure a lot of the logistics on how those problems are solved. So, I don't know. I would imagine that they had ways of doing that. It seems like they should be able to have ways of doing that, but I'm not positive. Any other questions about the historical stuff before we continue with the Turing machine stuff? Okay, so now just a note. We already mentioned it with the encoding of the polynomials, but let's make it very clear. Since Turing machines can only accept a string as input, any object we want to input into a Turing machine must first be encoded as a string. So if O is any object, we denote the string encoding of O with the brackets around it. And we take for granted that any object can be encoded into a string. For those of you with programming, you can think about a JSON string encoding of an object.
150 million combinations.
150 million combinations.
Which could be solved instantly almost with.
Yeah.
Which we can solve instantly almost. I'm just thinking.
Oh, okay.
Sorry.
What?
Anyways, so from here on out, we'll use this notation as encoding for a string. We'll do a concrete example encoding an object as a string just to make it extremely clear, but that's something we'll be doing. So, switching over now to this other whiteboard. Gonna pull this down. Make sure we back up some. That looks fairly clear. Alright, so let's do an example. Let A be the set of all the encodings of G, where G is a connected graph. Remind us of a connected graph. I know that we just kind of blasted through graph theory for like a half hour one day and then we kind of left it at that. But remember that a graph is just a bunch of nodes connected by edges. There's a graph. And we named the nodes. We might call it 1, 2, 3, 4, 5, 6. This is not a connected graph because it's not possible starting at one node to traverse it only along edges, getting to every single node. If I add some edges in, now it's a connected graph. Pretty straightforward. So, what are we going to prove? if A is a set of all encodings of a graph, where the graph is a connected graph, then A is a decidable language. We'll prove that we can decide this language. Or in other words, we can recognize every graph that is a connected graph and reject every graph that is not a connected graph. So we'll both accept and reject. We're not just saying it's recognizable, we're saying it's decidable. Notice that when we say recognizable, we just say except if blah blah blah, and that's it. Here I'm going to have to say except if blah 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 and reject if blah blah blah. Explicitly state when we accept and reject. Alright, so how does this thing work? Before we do it, let's just do a run through here with an example with G, and then go back and read this, and hopefully it makes perfect sense. So here's the actual mathematical definition of a graph, of a particular graph. G is an ordered pair, so we have a list here, start parenthesis, end parenthesis, an ordered pair with just two objects in it. The first object is this set right here, that's all one object. The second object is this set right here. Notice that this curly brace pairs with this curly brace. So it's an ordered pair, a list with just two sets in it, where the first set is a set of all our nodes. So 1, 2, 3, 4 are our only nodes, so I already drew those out. And the second set is a set of two element subsets of our initial set, and it represents edges. So if I have 1, 2 in here, that means draw an edge between 1 and 2. If I have 2, 3, that means draw an edge between 2 and 3. If I have 3, 4, that means draw an edge between 3 and 4. And if I have 1, 4, that means draw an edge between 1 and 4. So this is an encoding of that. This is a precise mathematical definition of a graph. Here's a pictorial representation of that definition. Now, if I wanted the string encoding of this thing, if we were talking about G, obviously we just do it with the string containing those characters. And that's perfectly fine. So encoding a mathematical definition is always trivial. Just replace its exact definition with the characters representing those definitions, or those symbols. Anyways, so what is our algorithm going to do? Our algorithm starts by selecting a node, doesn't matter which node. Say we start with node 4, and mark it. So we have a special symbol for a marked 4, which will be a 4 with a line through it. So we mark the 4. Then we search through here for any time that a 4 shows up in our edges. If a 4 shows up, mark off the thing paired with it. 3 is paired with it, so mark off 3. 1's paired with it, so mark off 1. Repeat every time we marked off a node. So if I did mark off a node, could have some flag checking, did we mark a node? Yes. Okay, then repeat. Now we're going to mark off all the nodes that have a 1 or a 3 or a 4 in here. So I search here, this has a 1 paired with a 2, mark off the 2. This has a 2 paired with a 3, the 3 is marked off, mark off the 2. This and that's it. Right? If when it's all said and done, we marked off all the nodes, accept. If we didn't mark off all the nodes, reject. Notice that if I had a 5 over here, then we would have put a 5 here. But now there's no edge connecting to 5. So as I went through searching my edges, I would have never marked off 5. So at this point, I would repeat it one more time. Wouldn't have marked off any new things. So then I just end. And now I just check this set. Hey, did I mark off everything? Yes or no? That's intuitively how it works. Okay, now let's read it from how I actually have it written here. All right, proof that A is decidable. What do? We design our Turing machine N so that on input, a string of G, where G is a graph, so this is encoding of a graph, select a node of G and mark it. For each node of G, mark it if it is connected to a marked node. Or in other words, it shows up here. Repeat step 2 until no new nodes are marked. If all nodes are marked, accept, otherwise reject. So there's a Turing machine that decides that language. Make good sense?
Yep.
Okay. And then, lastly for this chapter, a universal computing machine. What Alan Turing did. I told you in words that he built this machine, but now let me tell you exactly what his machine did. High-level description of his machine. What did it do? His universal Turing machine, and he describes this in all its states, all the detail, in his paper. He gives an exact description of this in the same way that we were doing Turing machines 2 weeks ago. actually listing out all the nitty-gritty detail. So he explicitly designs this machine U. What does it do? It takes as an input the encoding of a Turing machine and a string. So it takes the encoding of a Turing machine and a string. And remember, a Turing machine is a 7-tuple. Just like a graph is a 2-tuple, a Turing machine is a 7-tuple, and you can just convert that to a string. There's nothing magical about coming up with a string encoding of a Turing machine. He had a bit more clever way of doing it in his paper, but there's a stupid way that you could easily encode a Turing machine as a string. So encode the Turing machine as a string together with its actual input string. Where M is a Turing machine, W is a string. Then what does his machine do? It would run W on M. It would simulate running this input on this machine that you gave it. So you gave his machine, a different machine, and an input to run on that machine. And it would simulate this input on this machine that you gave him. This is like running software. This is telling a computer to run software. It's identical to that. So it's telling his machine to simulate this input on this machine. And then if the machine that you gave it accepted the input, then his universal machine would accept. And if M rejected the input that you gave it, his universal machine would reject. Now it's possible that M goes into an infinite loop and runs forever, in which case his universal machine would go into an infinite loop and run forever. So it doesn't magically make everything decidable. It could still go in an infinite loop if this goes in an infinite loop. Or it just goes on infinite procedure. Remember we talked about an algorithm when we were talking about the integers over there. Instead of having it, if you look at the first proof we did here, we said if we didn't do 0, -1, 1, -2, 2, -2, 3, but instead just 0, 1, 2, 3, 4, 5 forever, and never checked any of the negative numbers, and a negative number happened to be a solution, then our software would run forever. So if our machine runs forever on the input, then his machine will still run forever on the input. It doesn't magically figure out mistakes from our machine. That's the universal Turing machine. That's the second reason why his paper is so big, so famous, and that's the major reason that we credit Alan Turing so much more than we do Church. So chances are you've heard of Turing, chances are not so much of Church, unless you actually took computer science classes. All right, and maybe we'll call it there since that's the end of the chapter. Any questions you want recorded on lecture before turn off the camera?
This is a major shift from last class.
Yeah, I told you that we're gonna get to the fun stuff now.
I love the other stuff. But this is cool too.
Yeah, we're getting a lot more high level, and the more high level you get, the more complicated things you're able to talk about.
Mm-hmm.
If you require a lot of detail, you can only talk about very simple things.
Yeah, I feel like I'm almost like starting the class and now we're talking about it.
Yes, you could almost think about everything we did up till now is just like setting the foundations to get started.
Yeah, I feel like I'm
Yes.
starting again.
And so, yeah, some people I know, some professors that I watch the videos for, they just blast through the stuff that we did. They do that in like 4 weeks. 4 classes up to this point, so that they can hurry up and get started on this stuff.
I see. Interesting.
But the author of our textbook specifically does that. He just doesn't care. He doesn't even bother with any of the preliminary stuff that we covered. And that was a whole lot by itself. Anyways, yeah. Anything else? Cool.